I think it started now. Do you see that? Oh yeah, that's already
Yes,
seen.
sir.
Okay. So for the sake of completeness, let's put it in the recording. So we spoke about the water system and in the changing temperature and changing pressure situation and how the free energy of each of the components evolve, each of the phases evolve. And here it's slightly mistake is that it gives the energy a different P, and this should be gives the energy a different T, which we have elaborately discussed. And you can see in the last video the expanded images are there, but here of course it gives you a guidance on these slides. So when we take it to another single component system, which is iron system, is a very common one with regards to engineering solids. And here we would see how it's different, same for uh, a solid, a commonly used solid as well. So this phase diagram, this is what it's given in the pressure scale and it's given in the temperature scale. The pressure is in a logarithm scale, just to make sure that some aspects in the lower pressure scale is brought out clearly. Otherwise, it's pretty much the same. You can always make it linear scale and have a look at it. It's pretty much the same. So the question is it any different than some of the one component system that we've seen in the past, for example, in water system? And you see that there are phases like alpha, gamma, delta, liquid, and vapor. This is what the 5 phases is what we are seeing here. Now, if you look at it, alpha, gamma, delta are typically names or sort of, I don't know, it's not an acronym, but uh, sort of symbols given to different kind of phases of different crystallography of the same solid. All right. In a way, you could say that all of these things are solids. So to begin with, let's see if these are to be all solid phases, then I have alpha, gamma, and delta. All of these primary phase fields of these, that's the solid phase field. Okay. Then you have the liquid phase field, primary phase field for the liquid phase, and this is the line which is in the range of 1535 degrees Celsius. This is the line which has the biphase equilibrium or two-phase equilibrium, that's between a solid state and a liquid phase. And this one is the vapor, and this has equilibrium with the solid phases and the liquid phases here along this line. All right, and this is the 30, 3057 degrees Celsius, supposed to be the boiling point at 1 atmosphere. Why it is marked here? Because this is the typical boiling point, and we say that equilibrium boiling point, and that should coincide with some temperature, at 1 atmosphere pressure. So that's what we call is typically the normal or equilibrium boiling point. All right. So this is what the phase diagram is. But then, so in a way, it's fairly similar to what a typical one component phase diagram would look like. All right. And it's slightly different than water in the sense that, the solid and liquid two-phase equilibrium line is slightly on to the right. And if you look at it, this slope is less than 90 degrees. Okay, and in case of water, it's mostly, if you measure from here, it's more than 90 degrees, which is sloping towards the left. Other than that, it's pretty much the same. But in the yeah, okay. Could you please like mute your phone if you are not speaking? So here the interesting that comes in is that we were typically looking at solid liquid vapor phase diagrams, but then that's not all. You can actually look at different variants of the solids, right? But generally we don't have many different kind of structures in the liquid phase or the vapor phase itself generally, but we still have high density liquids and low density liquids, but that's for high classes when you go deeper into the structure of any material. But ordinarily, when we say that the liquid is one type of phase which has its own atomic structures and distribution of atoms and things like that, which typically is characterized by particular density for the component that we're talking about. But on the contrary, you can have solids of the same material, but in different forms. Okay, so this is what this region actually gives you some ideas about different allotropes that one solid might have. All right, are you guys aware of allotropes? I think you guys know it. All right, so we can have different forms of the same chemical composition solid. For example, you can talk about, I think the common example is carbon. Let's talk about carbon. Carbon, you can have amorphous carbon, some uh, nanostructured carbon that people have. You can have carbon black, that's one form of carbon. Like you have you get from burning of oil, you get that carbon soot. That's one form of carbon. You have graphite, which is kind of shiny, and then it's a good conductor of electricity, and thermal conductivity is high, and it's used in many different purposes. And at the same time, we have diamond as well. Diamond is also another form of carbon, but it's completely different. Okay, it's transparent, it's fairly hard, and it's slightly denser than graphite, and it's not a good conductor of electricity. Let's see. But then if you go deep down, then it's the same structure, same carbon. No, chemically, it's the same thing. But then what is it that is different in all of these materials, all of these allotropes, that they completely behave, and the physical and chemical behavior is completely different. That's with regards to their atomic structure, the kind of structures they adopt, their crystallographic order, or crystallographic structure, what kind of crystal class they belong to. Things change, and that it's a combination of thermodynamic variables, which typically would be of pressure and temperature. Okay, so in a single phase system itself, you can have different thermodynamic variables you can play around, and then manufacture different materials. That manufacturing is becoming very important right now, because people are trying to make, or they have made diamond from normal carbon sources. Diamond is, otherwise natural diamond is fairly expensive, but then to be able to use its beneficial properties like um, um, lesser electrical conductivity, electrical insulation, higher thermal conductivity, and hardness, people are using certain carbon sources to produce diamond-like carbon, DLC. Okay. Likewise, and that can only happen when you have a clear understanding of the pressures and temperatures and then stability of these phases vis-a-vis other phases of carbon. So this is the most interesting thing, and this is just an example of iron system. And the fact that you can have multiple phases and they are in equilibrium with each other at different combinations of pressure and temperature makes single component system and its study is extremely important, right? So here you could see that there's the alpha phase, there's a gamma phase, there's a delta phase. All right, and that means at certain temperature, from let's say moderate temperature, let's say room temperature, to about 910 degrees Celsius, you'd see that in most of the pressure ranges, alpha phase is the most stable one. Okay, and what is that alpha iron phase? Do you guys have any idea what's alpha iron? Anyway, you'll get that later. Alpha iron is pretty much the same iron, but then its crystallographic structure is different. It's all of these iron atoms are placed in a BCC kind of structure, body-centered cubic kind of structure. You guys aware of body-centered cubic? Or maybe there are studies on the next semester, but then in your +2 level, perhaps you might have studied something, which is, you talk about a cube. In the 8 corners you have 8 atoms, and right in the middle of the three-dimensional of it you have one, which is kind of gives you uh, five atoms in the cube. But then when you talk about uh, appropriating what is exactly there in the unit cell, you see that there's one in the middle and then 1/8 of each of the corners. That is for the share of the cube that you're talking about. So it's like two atoms per cube, 2 atoms per unit cube. Okay, so that's the BCC phase. So this alpha ion is actually the BCC ion. Okay, and then it's 9-10 degrees Celsius. It sort of sort of transforms into another phase, which is the gamma phase. Right? Now, gamma ion is not BCC. It's called austenitic ion, and that's an FCC phase. Okay, and what's an FCC type of crystallographic structure? Is unlike BCC, where you in the center of the cube you have an atom or lattice point. In FCC you have lattice points at the middle of the planes, the 6 bounding planes, instead of the three-dimensional center. All right, so in that aspect I'm not giving you a picture, so that because you'll always study it in the later stage, but then visualize this when I say in words. You have the cube, and in 8 corners you have 8 atoms of iron, and then there's nothing in the middle, three-dimensional middle. But what you have is you have 6 faces of the cube, and in the middle of the faces you have 1 atom of iron each. All right. In that sense, the number of atoms that you'll have in the unit cell is how much? Can you say? It's simple, it's 1/8 of each atom from the 8 corners. That makes you 1 atom. Plus, you have all the 6 faces. Okay, in all the 6 faces, since in the middle of the face there is 1 atom which is shared by the 2 unit cells, you'll have to take half of it. That means when you have 6 faces, you take 6 halves. That makes 3 full atoms. So you have 3 atoms from the faces and 1 atom from the corners, from the 8 corners. So 3 atoms from the 6 faces and 1 atom from the 8 corners. That makes it 4 atoms per unit cell. All right, that's the FCC structure. So this is FCC ion and this is BCC ion. All right. Now, why did I tell you all these crystallographic arrangements and then how many numbers of atoms are there in the unit cell? There is a point. All right. Now, if you look at the transformation here, all right, so what is this? This is the 9-10 line. Does it look like it's a completely vertical line?
No, sir.
No, it's not a completely vertical line. That means what? That means there is a little bit of a change in the volume that you might have. All right, change in volume meaning change in the molar volume. All right, so that sort of gives you an idea. So this is the denser phase, or this is the denser phase. It has more atoms here, right?
Gamma is the denser phase.
Gamma is the denser phase. Okay, so gamma is a something which is like what? Which is like the water system. If you look at this, just like this, here we are transforming the solid into water, but that's not important. We're transforming something which is a slightly rarer phase to a slightly denser phase, and that way it is on to the left. But of course we are missing one thing here. There is a clear distinction of the endothermicity of this reaction from ice to water. All right, on the density aspect we are talking about here. Okay, but that's compounded by the fact that there is a clear endothermicity in the transformation of ice from ice to water. All right. Here, it is not as important that the delta the change in enthalpy from the alpha phase to the gamma phase is not as distinct as you'd find in the transformation from solid water to liquid water, right? But then there's a difference in the density part, and that's one of the reasons that it is slightly on to the left. Going forward, when you go to about 3090 degrees Celsius again, this is, it's a denser phase, then it transforms into something which is called the delta phase, right? And the delta phase again is something which is a BCC, which is again a rare, less denser medium. Okay, this it's not a very common, what do you call, common phase of iron, but still it's a BCC phase, and this transformation makes the denser phase slightly rarer. Okay, and here we are talking about the reverse of what we are talking here. All right, and of course, since it's only the transformation between two solid phases, I would expect, I don't have the numbers to actually look up what's the enthalpy change, enthalpy change from the gamma to the delta phase. But then if that were to be a very small number, then you see that, this also is slightly on to the right, which is what typically happens from denser to rarer kind of transformation. All right, then we're talking about a BCC solid phase and a liquid phase, and its transition at about 1535 or 1545 degrees Celsius. That temperature can, some people write 1542, 1545 and all that, but doesn't matter. 1540 is that. Let's go for that. But then here we are talking about a BCC phase and a liquid phase of iron. All right, which is the denser phase and which is the rarer phase. Yeah. Anyone can anyone say? Are we recording? Yeah, we're recording. Yeah, typically, unless it's all the materials are not like water. So the solid phase to liquid phase would always be, to transition with the molar volume of the liquid is higher. All right, so that's why it's and of course there's no doubt on the endothermic nature of the reaction from the solid phase to the liquid phase. You have to supply heat to that. All right, so that's one of the reasons it's slightly on to the right. It's less than 90 degrees. This line, right? So it's like any other phase diagram that you'd find in the materials, that solid to liquid transition always go for higher volume or lower density transition, and since solid to liquid transition is always endothermic, mostly this line is onto the right. And of course you have vapor, which is in equilibrium with the different kinds of solid phases at these different pressures, and of course it has equilibrium with the liquid state at beyond certain type of pressures. All right, now if we have to draw the free energy diagram at this pressure across these temperatures, this pressure meaning simply normal atmospheric pressure, then we'll have the free energy curves which will look like this, where it's the sloping curve here. This is G versus T curve, and they will see that from this temperature, which is, the temperatures are not written here, room temperatures to about 935 degrees Celsius or 910 degrees Celsius. That's where the alpha form of BCC, yeah, it's written here. See, alpha is the BCC phase. That's the alpha phase, which is stable from normal temperature to about 910 degrees Celsius. And then comes the gamma phase from 910 to about 1400 degrees Celsius. From 910 to about 1400 degrees Celsius, it's the gamma phase which is stable, it's the FCC phase. That's why it is represented by this lower free energy here. Okay, and then about 1400 to 1535 or 1540 degrees Celsius, you have the delta phase, which is stable, again characterized by this curve, which is representative of the delta free energy diagram. And then of course beyond 1545 or 35, that's the liquid phase, which is stable, and this is characterized by this free energy curve. So we have distinct free energy curves of this liquid, which is like this, and then from 1545, no, it's about what, 3057 Celsius, then you have only iron vapor phase. Okay, it's beyond its boiling temperature at normal atmosphere. So this is the free energy line of the vapor phase. This is the free energy line of the liquid phase. This is the free energy line of the delta phase, which actually should look slightly more distinct, which doesn't look like it. And then you have the free energy diagram for the gamma phase, this one, and this is the free energy diagram for the alpha phase. All right, so what is written here is that the alpha and gamma phase, alpha and delta phase are a continuation of the same line, because of the fact that these two are BCC phases themselves. Just that from about 910 degrees Celsius to about 1390 degrees Celsius, these delta phases, they do not have the uh, minimum energy, and over which the gamma phase is more stable from about 910 to, but then otherwise it's the same. All right. Likewise, we can talk about a ceramic system, which is this one. All right. This is a system of zirconium dioxide. All right, it's one of the most important ceramic materials. It has many different applications in chemical engineering, in mechanical engineering, in high temperatures. It's a wonderful material. Okay, and if you go into its structures, then it's extremely complex. All right, there are several different structures. It's called the monoclinic structure, it's a fairly complex one. Okay, and then we have tetragonal structure. This is extremely important from load bearing point of view. And then you have a cubic structure, which is extremely important electrical, electronic and ionic conductivity kind of. Okay, and then you have the liquid phase and the vapor phase. Now you have these lines, which actually represent the monoclinic and vapor phase equilibrium, being made stable in the tetragonal primary phase field. Okay. Likewise, you have the vapor and cubic equilibrium. They extend into the tetragonal primary phase field. And likewise, you have tetragonal vapor phase, two-phase equilibrium. They go into in a metastable form in the cubic primary phase field, and likewise, right? So there is something called the T2M transformation. That you'll. I'm just what is it? I'm just telling you so that when it comes to you in future classes, it doesn't uh, appear to be completely new. T2M transformation is tetragonal to monoclinic phase transformation, which actually gives to us a slight change in volume. All right. So it so happens that this is from a denser volume to a slightly expanded volume. It becomes a monoclinic phase. All right. That has got uh, important applications in load bearing properties, or shock resistance properties, mechanical shock resistance properties. It can enhance the toughness of the body, the fracture toughness of the body, by exploiting this T2M transformation, right? uh, Likewise, you'd see that there's a subtle change in the slope, which is not exactly 90 degrees Celsius, I mean 90 degrees. And why is that? I give you a clue. You can study that. Okay, you can study that. Your job is to find out what is the enthalpy change in tetragonal to monoclinic transformation, what are the change in molar volume with the tetragonal to monoclinic transformation, and based on those two different points, two parameters, can you say whether this one is a 90-degree slope or it's bending towards the left or towards the right? That's your job to figure out, right? And you would see that the change between tetragonal and cubic um, is also, there's some differences there. It's not entirely 90 degrees because you know that the tetragonal phase and cubic phase are slightly different in the densities. But of course, the cubic to liquid transition is clear and straightforward, and cubic to liquid transition um, and endothermic reaction, and since it gives also to a phase with a much higher molar volume, then this is going to be it's going to bend towards the right. And of course, you have the vapor phase in here. All right. So the, these are the two, at least the two important aspects from technological standpoint is that T2M transformation. That's what we use all the time in advanced ceramics, and the C2L, the cubic to liquid transition, is from typical phase diagram point of view. All right. So likewise, you can have graphite, the phase diagram of graphite, and we can look at different aspects of it, because you know that in the conditions of higher pressure and longer time, of course the time is the kinetics part that we are not talking here, but at least you know that the formation of diamond is because of the uh, enormous pressure that the coal beds or the carbon phase has, and which actually gives rise to another form, a denser form, that's called diamond. You can actually do some calculations based on what is it, what's the kind of pressure that you require to make carbon into diamond. Can you synthetically produce that? That's the question. From a single component phase diagram is the primary ones that you read, and then you will go on to read more and more important phase diagrams. Two component system, three component system, even multi component system phase diagrams. But then the charm of single component phase diagram is still there, because that will help you figure out uh, what is it that it's kind of pressure temperature required, so that I can make um, diamond, okay, diamond films, or can I make pressurized diamond to the extent that pressurized carbon or coal or graphite uh, to a point that it'll yield diamond. And because that's kind of difficult to find naturally, because it's natural formation, and the frequency of finding a diamond, it's very low. That's why diamond jewelries are expensive. But then for commercial applications, can you synthesize diamond in laboratories or in engineering practices? So these numbers would give you a clue as to what is the kind of pressure that is required that we can produce diamond in the laboratory scale. Can you load up diamond to the point that at that pressure or temperature you can make diamond out of it? So these are some of the things that help you um, understand and sort of see what are the bells and whistles that someone has to do to be able to produce newer or interesting materials. All right, so I think we are done with the one component, single component phase diagrams. We'll go with mixing of solids. So what I'm left with is one is about chemical equilibrium, which is reaction equilibriums and gases and things like that, which I think will be done in one class, because you guys are already at some ease with solving questions and problems of gaseous equilibrium. You might have done some of it in 10 plus 2 level. So I think one or the max two classes would sort of suffice that. I think we'll talk about mixing of gases. That's an important part. And followed by mixing of liquids and the development of solution thermodynamics. When two different liquids mix, and then what are the characteristics? Can we, would they mix or would they sort of separate out? Uh, those are the aspects that we study. That will take about 6 classes or so. Right. And we are left with one more small topic, that would be the reaction between solids and gases. In particular, iron and oxygen, and metals and oxygen, because metal is the metallurgy part, and oxygen is, it's the oxygen, and what is produced is the ceramic part. So the metal reacts with oxygen, gives you a metal oxide, which is a typical ceramic, and we got to understand that part. So that is what is left. Another 7, 8 classes, or a little more than that. We'll see how it goes. Okay. So we'll stop the class here, and we'll take questions if we have, and then see what we can do next. All right, I'll stop the recording right now, and please let me know if you have questions.